quick, and I think you should be able to hear it.
Hello, my name is Jake Henkel, and my partner is Nicholas Garrison. We did our senior design project with my current employer, Parker Hannafin. We designed an automated pneumatic cylinder testing fixture for one of their assembly lines. We worked with faculty mentor, Dr. Rick Meyer, and industry mentor, Josh Kidder, who was our plant manager at the Otsego location of Parker Hannafin Pneumatic Division.
Some background on the pneumatic cylinder that we're testing. It is currently used on school buses to actuate the doors. It's produced by Parker Hannafin in Otsego, Michigan, and it's the highest production volume cylinder that they produce. The testing of this cylinder requires one dedicated operator, and the measurements that they take are subjective to the operator. The current manual testing process that operators use is they insert a lever actuated air supply connector into the ports of the cylinder, and then they manually control the extension and retraction of the cylinder at both high and low pressures. And then they also measure the lengths of the rod extension with steel rulers, and then lastly they monitor the pressure with an analog pressure gauge.
This leads us to our problem statement. Current cylinder quality testing is not consistent, lacks accuracy, and requires the additional cost of a dedicated operator. This operator looks for the following testing characteristics: verifying orientation of cylinder body, ports, and eye bolt. They verify correct piston rod lengths after extension and retraction at both 20 psi and 90 psi. And lastly, they check for leaks in both extension and retraction at 90 psi. Our goal is to automate the entire testing process. Our fixture will complete all the product characteristic verification processes, and as a result of that, it'll reduce the head count in the assembly line by 1. It'll also improve the measurement accuracy, and lastly, it'll reduce any operator fatigue.
Before we talk about the design of individual components of the fixture, we'd like to show you a video of the fixture running a cylinder through the entire test cycle process. Hopefully this helps you gain a better understanding of how these systems are working with each other and provides a clear idea of the end goal that the design was attempting to achieve. Once the operator presses the start button, the air delivery nozzles engage the head and the cap of the cylinder. The cylinder is then extended at 90 psi to make sure it extends to the proper length, and then retracted at 90 psi to make sure it retracts to the proper length. Once these lengths are verified, the cylinder piston rod then extends at 20 psi to make sure it fully extends in a low pressure scenario. Then retracts at 20 psi to make sure it retracts fully in a low pressure scenario as well. Then we need to test the pressure. 90 psi is applied to the cap side of the cylinder. The air is shut off and the air system is allowed to settle before an initial pressure test is read. After that initial pressure is read, it waits 15 seconds for a final pressure reading, verifying that the final pressure is at least 99% of the initial pressure to pass. Once this happens, the head side pressure is then read. The same process follows. Once all characteristics of the test have passed, the fixture begins its shutdown sequence, venting the air and disengaging the nozzles. Displaying pass, the operator is able to remove the cylinder and then replace the next cylinder, and the system repeats. Now that you've gained a more general understanding of how this fixture works and its purpose, we're going to talk about the fixture design. Our design goal for this fixture was to improve the measurement accuracy and repeatability of our testing process for this customer. The first iteration of the fixture design included actuators for the air application nozzles located externally from the head and cap trays. This presented a problem in introducing forces and torques onto the carriage rails and introducing error and wear into the design over time. Making a one-piece housing for the head and cap trays kept these forces internals and fixed the issue of iteration 1. The main issue of iteration 2 was now that this head tray, the one that moves on the right side of the screen, is a little top heavy and may introduce error when measuring the cylinder length and early wear. Creating a tray that had a carriage rail running through the center eliminated the issues presented by iteration number 2. And now in iteration number 3, we're starting to introduce our position sensors. However, in this case, the line of action in the position sensor is just too far away from the line of action of the piston rod, and we were afraid we were not going to be able to get as accurate measurements. After another design change, we determined we were unable to get the position sensor close enough to the line of action of the piston rod. This, and a desire for increased sensor resolution and durability, led us in a different direction. The 5th iteration of our fixture design incorporated magnetic position sensors for the cylinder body length, extended and retracted piston rod length. This resolved any issues due to wear, as there are no moving parts, and provided us with the increased resolution that we wanted. The Otsego location of Parker Hannafin has its own tooling and machining shop, allowing for these custom designed parts to be machined in-house free of cost. This slide and the previous slide depict the two-dimensional drawings required by the machinist to create these parts.
The way we deliver air to the cylinder in this fixture is through a pretty simple lever system. We have a small pneumatic cylinder here in black that creates a force that we call the F actuator. This force is about 159 pounds, and that translates to a force of about 177 pounds on the other end of the lever. We called that force F applied. Opposite of this force is F air pressure, and that's about 27 pounds. And on this nozzle, there's an O-ring that seals against the machine surface of the cylinder. And since F pressure is significantly lower than F applied, that guarantees that we'll have a seal during the testing process. The 3 reference surfaces highlighted in this slide are critical to the function of our fixture. These surfaces allow us to accurately measure the body length and then also the piston rod extension and piston rod retraction. These 3 surfaces are made from hardened steel so that during regular use they do not wear down easily, and it will allow us to produce repeatable measurements from cylinder to cylinder. Now we're going to discuss the sensors in our fixture. First, we will look at 2 microswitches. The switches will detect the presence of a cylinder as well as verify the correct orientation of the head and cap. The flat surface shown on the cross-section below will activate the switches and allow the program to start. The orientation of the 2 switches varies due to how the cylinder is loaded into the fixture. This minimizes any damage to these switches. In addition to the 2 microswitches, we have a 3rd microswitch as well as 2 proximity sensors that are performing a similar task. These sensors verify the correct orientation of the cylinder body. If you look at the cross-section on the right, these sensors will get activated by side 4 if it is in the incorrect position. Looking at a cross-section of our fixture, we can see in position 4 the rail of the cylinder body highlighted in green. This shows the correct orientation of the cylinder body. If this rail were to be in position 2, a microswitch would be activated. This microswitch would then tell the PLC that the body rotation is incorrect. If the rail were to be in either positions 1 or 3, one of the arms highlighted in yellow would be actuated. When actuated, a cap screw gets pulled away from a proximity sensor. Once the sensor can no longer recognize the presence of the ferrous metal, it will alert the PLC that the cylinder body rotation is not correct. Looking at the image on the right, you can see these cap screws on the arms down here at the bottom, as well as our micro switch that's housed in the fixture. Our programmable logic controller is capable of reading 0 to 10 volt analog inputs. It'll translate these voltage values across a 4096 bit range. The analog inputs that our fixture uses are our position sensors and also our pressure sensor. The position sensor has a 4.25 volt range, which is 1740 bits.
The sensor length is 2.95 inches, so that translates to 1/2000th of an inch per bit. This allows us to accurately measure the tolerance of our body, which is plus or minus 30 thousandths, and also the piston rod extension and retraction, which is plus or minus 60 thousandths. Our pressure sensor has a 0 to 10 volt range, so this will make use of all 4096 bits, and it can read air pressures from 0 to 100 psi. This means that we can read 0.025 psi per bit, which is 1/40th of a psi.
This graph depicts the linearity of the position sensors used in the fixture. The y-axis displays the PLC bit values that were recorded when the fixture reference surfaces were set to the appropriate positions using calipers. The gray line shows the results of the body sensor, the blue line shows the results of the piston rod sensor in the retracted position, while the orange line shows the results of the extended piston rod position. Each cluster of points on each line represents the 3 different length configurations of the cylinder, with each point of each cluster representing the minimum length tolerance, the design length, and the maximum tolerance value. As you can see, the R value calculated for each of these datasets is very close to 1, meaning that if needed, the bit values can be confidently extrapolated if any new bounds needed to be set. The slope of these lines is also displayed, showing experimentally the number of bits per inch and validating the sensor resolution of 0.002 inches. When deciding on which PLC to use, it was determined that the Allen Bradley Micro 820 was the right fit for our application. This PLC is able to accept both the analog and digital inputs necessary for the fixture operation, and also features an LCD display that can be programmed to communicate where the fixture is at in the testing process. This particular model of PLC is able to be programmed using the free downloadable software Connected Components Workbench, which uses a form of programming called ladder logic. The pictures to the right display a few examples of the ladder logic program that is used to measure and analyze pressure and length readings to then execute the program on the appropriate path to either pass a cylinder or display the corresponding error code on the LCD display. To show what happens in the instance that a cylinder is out of tolerance, we will show a video of a washer being placed between the reference surface and the end of the piston rod. The width of this particular washer was measured to be 0.0695 inches, which is just above the allowable maximum tolerance for the length of the piston rod. As you saw, the cylinder did not complete a full testing cycle and instead displayed a red screen with the text WF long. WF is the name given to the dimension representing the length from the top of the head to the end of the piston rod. After the cylinder is rejected, the operator is able to quickly set that cylinder aside, knowing what corrective actions need to take place to fix that issue.
We performed a brief analysis on the piston actuation. We did this to see if the time it takes to actuate cylinder multiple times in one test will start to play into the overall process time. We started with the Hagen-Poiseuille equation. This was discovered experimentally in 1838, but it can also be derived from the Navier-Stokes equation. This equation describes volumetric flow through a round pipe. It also assumes that the flow is laminar and that this pipe is at least 48 times longer than the diameter. So once we calculated our volumetric flow, we were able to find the velocity of our piston by dividing it by the cross-sectional area. From this, we can divide the length of our stroke by the velocity. This will give us the time to extend and retract. We found that this time was very short, so it was negligible to the entire process. But because of this, the cylinder is actuating very fast. So we installed some flow control valves to minimize any damage to the fixture or to the cylinder itself. Some shortcomings of this was it didn't really account for the static friction of the cylinder. These cylinders have a significantly higher static friction when compared to the kinetic friction.
This is the bill of materials for the project. The total material cost was $2,446.86. This created an estimated annual savings of $825. This is based off an annual volume of 1,650 cylinders per year. We have some recommendations for this project going forward. Since this fixture has moving parts, we recommend that safety guarding is installed prior to routine use. This will minimize the risk of any injury to an operator working with the fixture. Next, we'd recommend comparing the pressure drop and length measurement values to the manual test results before being fully implemented. Next, we'd recommend that calibration diagnostics are performed quarterly. This will ensure that the measurement values are accurate. Lastly, we'd recommend that the operator that's freed up from this process is used to increase production of other products elsewhere in manufacturing. To conclude this project, the fixture solves the known issues associated with manually testing pneumatic cylinders. It reduces the head count on the assembly line from 6 people to 5. This allows that one operator to be more efficiently used in other areas of manufacturing. And the most important conclusion we have is that the measurements are no longer subjective to the operator. The fixture can measure much more accurately and much more consistently. We believe that this will lead to additional savings due to minimizing the risk of shipping out underperforming parts to customers.
Okay, so at this point, we'll take any questions that you have.
Presentation is open for comments and questions. Maybe I can ask question, so we wait for another ones. You analyze 5 iterations. It's very interesting. Can you identify dominant or most influential variable when you rate your iterations?
Yeah, so as I mentioned, I think around iteration 3 or 4, being able to get that getting the actuator to be one piece with the tray to keep all those high forces internal. As you can see, that the actuator produced a force of about 159 pounds. So having a lateral force on a carriage rail that's small in size like that could produce wear over time, and keeping the resolution of those sensors low and ensuring that no damage to the sensors occurs by having a magnetic position sensor where there are no moving parts was definitely a big factor in those iterations.
Thank you. Other questions, comments? If there is no more comments or questions, thank you very much for all presenters in this section. This concludes our morning session of session A, and we will start presentation in afternoon and 1 o'clock. Again, this session was very successful. In some presentation, we have over 40 audience in this presentation. Thank you very much for this successful session.
Thank you.
Thank you.